My name is AJ Bayat, and I chose to do Bloom filters for my extra credit assignment for Computer Science 223. So moving right into it, a Bloom filter is what is classified as a probabilistic data structure, and a Bloom filter specifically uses multiple hash functions to fill a bit array to allow for a user to check if membership is present. So basically it uses two types of methods, the hash set and the bit set, which we will get into, to fill out an array and then compare the values to check if that element that you're searching for is within the array. But first, a probabilistic data structure won't tell you exactly if it's in the array. Instead, it'll give an approximate estimation of how likely it is that that element that you're searching for is within the array. So for instance, it might give 96% in the array. Depends. We'll get into that. The benefits of this is we're able to lower our memory usage without increasing our runtime too high. And so general use cases aim to just balance memory and runtime. But some use cases might either be categorized as compressed or optimized, whereas compressed might value memory more, so you want to save as much memory as possible, use as little of it as you can, and you don't really care about runtime. Hence it's compressed, you have to compress it and decompress it, increases the runtime. Optimized, we don't care about how much memory we use, we want to use as much as available, we just want it to be as fast as possible. But probabilistic aims to find a middle ground between compressed and optimized, where we want the benefits over standard in that we use lower memory, but we don't let our runtime go too high as to impede with what we're trying to do. The first step of checking for membership within a data set that we're all taught, the first method is linear search. And it's just simple. You just take a set of numbers. For this I have 1, 3, 4, and 8. And let's say we want to find number 8. Well, we traverse the whole set, compare 1 to 8, not there, 3 to 8, not there, 4 to 8, not there. Get to 8, we mark it as found, we return it, that's it. But there are issues with linear search, as I'm sure we all know. If the set of numbers just keeps getting bigger and bigger and bigger and bigger and bigger, comparing an element like this to find it in this array would take a long time, and as such our runtimes would go up. There are other implementations such as binary search, which do help improve over linear search, but they still run into the same problems in the fact that they will degrade eventually. Eventually you'll get a data set that's too big and it'll just cause runtime to skyrocket. So probabilistic data structures such as Bloom filters can help with this. And the first step of this is just a hash set. So simple hash set. For this I have 2, 5, 7, and 8. And you just take a hash function, hash it into this array. The hash function for this example isn't too relevant. Just it places it in the array. And so we have 2 goes here, 5 goes here, 7 goes here. And in the event of a collision where we want to hash 8 into the same spot where 7 already is, we'll probe the next one. It's empty, and we'll put 8 there. So now, when we want to find 7, we simply just use the original hash function that we used to insert them into the array, and just search for 7. It's there. Boom, found. Want to do 8, goes to 7, same as before. It'll correct itself. For the collision, boom, found. But if we want to do 9 and it points to 8, it'll first check the item in the bucket and then compare it to the find value. And then since it's the 8 is not equal to 9, we'll probe the next bucket and to 0, so we know that this 9 is not in our data set, return not found. while hash sets work great for increasing lookup performance, it also causes an increased need for memory. In my example, we didn't really need to, but you may need to double the size of the array. You may need to rehash constantly. You may need to rehash. It just adds increased need for memory as it increases. But the other part of a Bloom filter is a bit set array. So for this, you just take the elements and place them into their indexes. For this, we have a 16-bit array, and all of this can be fit on 2 bytes. So we just put 1 in the 2 in, or just 1 for everywhere that we have a number in our data set, the corresponding index. But the issue with the bit set array is that if we have a set like this, where we have a set of numbers and then a big gap, and then our next number that we need, we end up with an array that looks like this, which obviously isn't ideal because we have to store all of those zeros, which are basically irrelevant to us, and it's just an unnecessary use of memory. It's very inefficient. So this is where Bloom filtering can come in and combine the hash set and the bit set to create a nice, elegant middle ground. So for this, we'll take a 32-bit array, which we would need 4 bytes for, and we'll take the same set that we were using for the bit set of 2, 5, 7, and 8, and we will begin by using the hashing function, but this time we will increase it to use 2 hashes. So it'll do a hash function for 2 when it inserts it, and then a second hashing function for 2 when inserted again. So we will end up with 2 corresponding to 2 locations within this index of arrays, or this array of indexes, sorry. And we do this for all of them, passing all 4 of our data set through the same hash functions. And then let's say we want to find number 7. We obviously know it's within our data set, so we pass 7 through hashing function 1 that we used, and we see that that is a 1, so it's a match. And then we pass it through hashing function 2. We see that that is a match. Because both are 1s, we can mark it as found. We know that 7 is within our data set. Now, if we try to find 13, which we obviously know is not in our data set, by coincidence, let's say it probes us here, and we see that there is a 1 in this index, well, then we would hash the second function to see that this is a 0. Because both are not 1s, 1 is a 0, we know that this 13 is not within our data set, so we can mark it as not found. Now let's take for 22, and by pure coincidence, hash function 1 and hash function 2 give positive matches for 1s. This is where the probabilistic nature of the Bloom filtering comes in, and this is what is known as a false positive, because we know that this is not within our data set, but it is showing that it is. This is not ideal, and false positives can be accounted for by using this formula. So for our example, we have a 32-bit array. We use 2 hashing functions, and then n for the formula is the number of elements that were in our data set. So we use 2, 5, 7, and 8, so that will be 4. This gives us a false positive rate of about 5%, which isn't too bad, but it's not very ideal, and we'll get to that. So if we increase the number of data set elements, we can see that our false positive rate goes up, which is not good. We want that number to be as low as possible, but obviously, as you fill up the array, every number is going to show a 1, and eventually, if they all show 1s, every number is going to be basically a false positive, because you're not going to know which numbers are true. So that is one of the main downsides of this data structure. See, as we just keep doubling the number of expected elements, our false positive rate just keeps going up. And even if we increase the number of times we hash, we still see our false positive rate going up. But if we increase our bits that we use, the size of the array, obviously there's more spots where there will be zeros and ones for each element to match up to that. So this lowers our false positive rate back down to 15. But you would think that even if we lowered our number of hash functions to 2, it would lower, but it doesn't. Our false positive rate is still 15%. It's just very unfortunate. So if we increase our bits again and we use 3 again for our number of hashes, we can see that our false positive rate goes down to 5% and then 3%. So all of this is kind of saying that it's not very intuitive to know how many bits or how many hash functions to use depending on your expected number of elements within your data set. So there are methods to calculate that, for which these are the formulas with the corresponding elements. N is the number of data elements, M is the bits. So we can find our ideal number of bits and hashes to do. And if we choose our false positive rate, we want something about 1%, let's say. And we use our number of data set elements that we were using from our last example of math that we were doing. This one. We can see that the best number of bits is 154 and the best number of hashes is 7. While 7 does seem high for the number of hashes, the takeaway here is that it uses an extremely small amount of memory. So while the hashes may be computationally taxing, you can use hashing tricks to further enhance that area of the data structure, which goes beyond the scope of this assignment. But there are multiple hashing. You can use quadratic probing. You can use whatever you want to increase the performance in that area. But the benefit to this, again, is just that it's a very small memory footprint compared to others. And because you usually only hash about 2 to 7 times, the time complexity is the number of times that you rehash. So because it's only 2 to 7 times, it behaves more like linear because it's O of 1 or constant, sorry. And the space complexity is just the size of the array. As the array gets bigger, the space gets bigger. And that's everything. Thank you. So bloom filtering has many real-world uses. Using the same example I give, you could use it in networking just to see if you have access to a server. You could check bloom filter, does he match? And if he does, then you allow him access. You could use it for databases and storage. It cuts down on caching. You don't have to store data sets like I did with numbers in my examples. You could use examples like of a list of food that you like, name it banana, apple, tomato, and have those hash out using the hash functions that you want to use and place those in an index. And when you search is apple in there, it should give out the same result. A thing that I found interesting when researching this was that Chrome used to use bloom filtering to check for malicious URLs. It used to compare with the URL you entered with a list of malicious URLs to see if they matched. Cryptocurrencies benefit from bloom filtering by cutting down the need to download the entire blockchain, so they can only need to download the bloom filtered parts, which are the parts that are relevant to them, because all the other stuff is unnecessary. Um, so they only need to check, is this in there, is this in there, is this in there, and they can get back what they need, which significantly reduces bandwidth across the internet for that alone. And spell checkers even use it in a rudimentary way just to see, like, is this word in the dictionary, and comparing it that way. Aside from that, I have my references. ChatGPT was used at the very beginning just to form some understanding. Geeks for Geeks had very in-depth descriptions. The second one was very helpful, had a lot of great pictures, and the two videos really helped solidify my understanding. I probably watched those videos 20 times. Thanks for watching.